Yes, now I click on go live on YouTube, and I'll make sure that things are on live on YouTube side, and I'll get started.
That is so cool. Okay.
It took some time to figure out all the configurations.
Oh, like a config.
Yes.
And
yes, it's now on live.
I believe I'm sharing my screen. Hopefully y'all can see it.
Yes, I can see. Yes. All right.
Hopefully...
We are sorry for the delay. And let's get started. So welcome to 3DGV. We have yet another truly exciting session today. We have Noah Snavely from Cornell Tech and Google Research giving a talk, joined by two panelists. The first, Pratul Srinivasan, rising star in 3D vision, joining us. And also a legend, I would say a legend in 3D vision, Rick Zelsky, also joining us. So Noah got his PhD from University of Washington under the supervision of Rick Zelsky and Steve Seitz, and then moved to Cornell. He got many awards, NSF Career, PCASE, Microsoft New Faculty Fellowship, Sloan Fellowship, SIGGRAPH Significant New Researcher Award, Best of Time Awards, Best Awards, and so many. So I don't have to really introduce. And I also have many good old memories with Noah. I can keep talking 10 minutes, 20 minutes, but I just shut myself up and pass to Noah for the talk. So Noah, it's all yours now.
This is so cool. Thank you so much, Yasu, for the introduction, and thank you all for attending, and hope you all are having a good day. So I'm going to talk about, I guess, a set of projects that I've been thinking about under the umbrella of the Plenoptic Camera, and I'll talk about what that means in a few minutes, but and hopefully y'all can see my slides. I think we have all the tech worked out. But just to motivate, a big goal of graphics and of other areas like photography and art in general is to capture and depict the world in ever more realistic and compelling ways, right? So, throughout history, people have used whatever media was available to them to do that. Whether it's perspective, correct painting in the Renaissance and later, or photography starting in the 19th century, or stereo photography, where from your living room you can put this stereo photo of the Pantheon in your stereoscope and feel like you're really in Rome. All of these are kind of great technologies that seek to do this, and I can name other things like VR more recently. In a lot of ways, some of my favorite projects in this vein are ones that try not to just capture your pantheons of the world, famous landmarks, but try and capture the entire world or big chunks of the world. So one project that I really like, which I think is underappreciated which has the spirit, is called the Aspen Movie Map. So Aspen Movie Map, if you're not familiar, is a project from the late 70s and early 80s from MIT Media Lab, folks like Andrew Lippman and Michael Nymark, where they wanted to capture the city of Aspen, Colorado, and then create an interactive experience around that. So this is basically Street View, but 30 years ahead of its time. They did a Street View type thing where they attached a camera to a car with an anamorphic style lens, and they then captured all this data onto optical video disc. I think that's the same as a laser disc, kind of new technology at the time, and then create an interface where you can explore. You can drive through Aspen yourself from your home. And here's a little video from showing that interface. It's a very vintage style experience. It has all the buttons you need to turn corners and drive through Aspen and experience what it's like to be there. It's truly visionary and amazing project. And if you think about capturing a place, it's kind of not enough to capture it once, because places change over time. So they thought of that, and they captured both a summertime and a wintertime. You can toggle between different seasons. Lots of kind of pioneering ideas in this project. Here's what the first page of their SIGGRAPH SIGGRAPH 1980 paper looks like. It's all great. Very good. So if you take this idea and, I guess, take it to its logical conclusion, what you arrive at, this idea of capturing everything, you arrive at this idea of the plenoptic function, which is, this was described by Adelson and Bergen in their, landmark 1991 paper. But the plenoptic function is a hypothetical function representing everything you could see And by the way, these slides are from Alyosha, great kind of description of it. So you can think of this as maybe one way to parameterize it is this Plenoptic function as a 7-dimensional function where, okay, you've parameterized rays in the world. So they have a location, x, y, z, and a direction, theta, phi. They have your light has different wavelengths. You have wavelength lambda, and you have a time t. So you can dial up any position in time and direction, and the Plenoptic function will tell you what you would see along that light ray, the radiance. So if you could capture that function and store it, you could reconstruct any view at every moment, at every position on Earth, I guess throughout the universe, more generally. And correlates that contains every photograph, every movie, every home video, everything that anyone has ever seen, and it's a complete description of our visual reality. And somehow this is like an aspirational type thing in computer graphics. If you could somehow capture and replay this function, it would be you could teleport anywhere at any time. You could go to the savannah. You could stand in Rome in the at any time of day, so on and so forth. And of course, it's completely hopeless to capture and completely hopeless to store, and sort of just a hypothetical thought experiment. But you could try. So if you wanted to capture the Plenoptic function and its all of its grandeur, there's a few tools that have actually been making huge strides recently that you could think to use. So one is light field capture. So over the last 5 or so years, there's been advances in light field cameras. There was the jump camera from about 5 years ago for capturing stereoscopic 3D, stereoscopic 360 video. More recently, Paul Debevic's team at Google has built, and others in the world have built ever more kind of, complex and high quality camera rigs. And so you can get pretty good VR video. And I know this video will probably be a bit jaggy over Zoom, but we can do we're pretty good these days at kind of headspace volume view synthesis, even for time varying scenes. Okay, and this is an example of that. So you can imagine, putting a jump camera, sprinkling jump cameras all through space and recording, recording everything as a way of capturing the Plenoptic function. But that really doesn't scale. You can't sprinkle the universe with cameras. So instead of capturing everything, in some sense, we're forced to sample and reconstruct the Plenoptic function in a smarter way. So one way to do that is, instead of having stationary cameras throughout the universe, drive cameras through the world. And that harkens back to this Aspen Movie Map and Google Street View idea. You have mobile cameras driving everywhere, capturing everything. And maybe in some sense, Street View is the closest thing to a Plenoptic camera that we have today. There's massive geographic coverage, probably millions of miles and billions of images captured by this point. But it still represents a very sparse sampling of this grand Plenoptic function. So if you think of what the Street View cars do, they'll drive through some street in the world. At one point in time, they'll probably capture a panorama every 5 meters or so. So fairly sparse in space. And maybe, I don't know, 6 months, a year later, they'll drive by approximately the same place, maybe the opposite side of the opposite lane, and again capture the sparse sampling. So somehow, despite how huge Street View is, it's still very, very sparse if you think about it in this kind of Plenoptic function way. Okay, another thing you could imagine is a way of capturing the Plenoptic function is using everybody's camera as your distributed camera. So maybe all photos on the internet could represent a dense sampling of the Plenoptic function. And I think for landmarks like the Trevi Fountain, a place I've worked on for a long time, you get a pretty dense set of photos. So here's like a, this is from the Rome in a Day project, 10-year-old 3D reconstruction of the Trevi Fountain from, I don't know, 1,000 photos or so. So you can get pretty dense, relatively dense spatial samplings. These photos kind of cover, these photos are pretty dense. But if you think of them as spatiotemporal samplings, it's again very, fairly sparse. So you may have one photo taken on July 1st, for instance, 2010. one photo to cover that whole day. So still very sparse, despite kind of how frequently people take photos of places like this. Okay, so if you step back and think about this as a general problem, in all of these cases I've described, we're given a sparse samples of images at different locations in time. So you can think of images as samples parameterized by XYZ location and time. So we have a bunch of images at XI, samples XI, YI, ZI, TI. And we need to somehow take these samples. If our goal is to do plenoptic reconstruction, we have to reconstruct the plenoptic function from these samples. So, interpolate any new image at any new place and time. And so I think we're at a point where, like, finally, computer vision and graphics has good tools like, deep learning, neural rendering, et cetera, and good data for this reconstruction problem. And so, that's kind of prime time to tackle some of these challenges. Okay, so I'll talk about two different projects in this vein. Plenoptic reconstruction at landmark and city scales, corresponding to kind of internet photos and street view style photos. And I kind of use plenoptic function loosely. Like, I think literally it would mean it'd be like the kind of, I don't know, worst surveillance camera you could ever imagine, like, recording people in cars and everything. So we're not going to try to model dynamic objects like that. So you can think of what we want to reconstruct is like long exposure photographs where all the moving objects are blurred away, but you can see what a place looked like at any given time of day and any given time of year, etc. Okay, so with that, I'll start. So let's start with the kind of landmark scale reconstruction. And this is work at Cornell with my PhD students, Jungqi Li and Wenqi Xian, and new Cornell faculty, Abe Davis. And actually, Abe put together such a beautiful video, because he's the master of videos and After Effects, that it would be, I feel, criminal not to show part of the video he made. So I'll start with and hopefully I'm sharing the sound, so you'll be able to hear Abe narrate too. Let me know, please chime in, some organizer, if you can't hear it. Okay.
Crowd sampling the Plenoptic function by Zhenqi Li, Wenqi Xian, Abe Davis, and Noah Snavely. Most of us carry a camera almost everywhere we go. Nowhere is this more apparent than at a popular tourist attraction, where you'll often find as many cameras as there are people. And this leads to a lot of photos, which we can think of collectively as the result of a kind of crowd sampling over time. Now, a lot of those photos eventually get posted online, where they become freely accessible to anyone with an internet connection. So in this work, we explore how to use that crowd-sampled data to turn regular photos into something that lets us move around a scene, both in space and across changes to appearance that happen over time.
Okay.
Crowd sampling.
Wait, thank you, Abe.
Crowd sampling the Plenoptic function.
There we go. Okay. So, so let's think about this reconstruction problem in this case. Okay, so if you imagine, let's simplify this Plenoptic function as being 2D. So, x is time and y is viewpoint, just one dimension of viewpoint in the simple cartoon. So, and the Plenoptic function is for each point in the space represents an image, and the Plenoptic function would be this entire space of images. Okay, so if you think about a column in this 2D space, so a fixed time but varying viewpoints. If I had a sample of viewpoints and I want to reconstruct that column, that would be a kind of a view interpolation problem or a light field rendering problem. Okay, if I think about a row of samples in this space, so these are images from a fixed viewpoint taken over time. If I have samples like that, then somehow I have like a time-lapse synthesis problem, like generate a time-lapse video from sparse samples kind of problem. But what I have in this internet crowdsourced, crowd sample case, photos I'm getting from Flickr, I have random samples in this plenoptic space, random samples of images. So each point again represents an image, and I want to reconstruct, sort of this full 2D space from these samples, and even more, maybe more concerning than the sparsity is that timestamps on photos are very unreliable. So I don't even necessarily know how to localize these photos in time. So usually like the date you get from your exit tags is good, but the timestamp, it could be set to your clock back in New York City and you're in Rome. Okay, So we have these kind of loose, very, very unstructured samples of the Plenoptic function. Okay, so what we do is we fit a scene representation that's able to capture the diversity of appearance and let you dial in appearance and also change the viewpoint at the same time. And so I'll let Abe explain that a little bit more.
So to address these challenges, we introduce a new neural scene representation called deep multiplane images, or DeepMPIs, which offer a way to represent viewpoint slices of the Plenoptic function that interpolate meaningfully between changes of appearance that happen over time.
Right, so here you can see on the right-hand side, the viewpoint changing and the time changing simultaneously. Okay, so, and again, the way to think about this is we're downloading a bunch of photos from Flickr of the Piazza Navona in this case. There's a lot of great landmarks in Rome that I love to use for view synthesis. You kind of put them into a big grinder that gives you something called a DeepMPI. And that DeepMPI encodes somehow all of the different appearances that are possible at the scene. 12 o'clock on June 1st, 7 p.m. on April 17th, et cetera. From which you can render, you can kind of dial a specific appearance as well as change, see it from different angles. Okay, so let me explain how this works. Okay, so we start with crowd sampled photos, thousands of photos of a landmark, reconstructed with structure motion. We use Colab from Johannes Schoenberger. Here's a point cloud and reconstructed camera positions. And then we build on this MPI idea, these multiplane images, which are representations of 3D that represent scenes as planar slices, each planar slice containing an RGBA image. So this visualization is from John Flynn's work. But this idea actually goes back to more than 20 years to work. Okay, Rick is here. Rick and Paulina Goland used this idea to do stereo matching in ICV 1998. Actually, I believe this was a Mar Prize runner-up winning paper. And they called it a stack of acetates, but it's essentially the same thing. Planar images arranged at varying depths from a reference view with RGBA content painted on each. And so, this is very much in the spirit of layered representations in graphics and vision, which themselves have a long history. Like Wang and Adelson worked on this in the early 90s as well. Kind of layered representations for representing parallax in scenes. But in fact, in some ways, this idea of representing scenes on multiple planes goes back even earlier to the work of the Disney Corporation, starting in the 1930s, where if you want to simulate 3D effects with 2D images, which is what usually your animations are painted on 2D on flat surfaces, and you want to simulate it in a simple way, they came up with a technique where you can arrange content on different transparencies stacked, arranged in kind of stacks with the camera looking down. So there's kind of a stack on each of these planes, of transparency in each plane. There's a camera looking down. And by translating the planes at different speeds and taking a picture as you go, you can kind of have simulate 3D effects similar to kind of parallax scrolling in video games. So here's kind of a example, the moon's at the far plane, other content, like the houses in the nearer plane, and you can simulate 3D effects in this way, very nicely. Okay, so we take this idea, the stack of acetates or multiplane camera idea, and computationally, what this defines what we call a multiplane image. So we have a reference viewpoint. We have a stack of transparencies arranged at different depths, virtual images arranged at different depths. Each of them has a RGBA. Each of them is an RGBA image, so RGB with transparency. And so to render a new view using this representation, you simply apply, given a target viewpoint you want to render to, you apply the appropriate homography to each layer, and then overcompose it to form an image. And this kind of multiplane, here's an example for the still life with banana scene. Actually, I shot this at Cornell Tech. So you take all these layers, if you arrange them in 3D in the right way, and then zoom into the reference view, the content coalesces into a very nice 3D view synthesis experience. Okay. So these are quite nice, these multiplane images, because they model disocclusion. You can represent stuff behind other stuff. You can even simulate non-Lambertian effects, and they're simple and differentiable, so very nice for kind of deep learning approaches. Okay, so your standard multiplane image, your standard MPI, has a voxel-like volume where each voxel has an RGB color and an alpha value. Okay, RGB and how opaque that is. And you can fit these to any scene like the Trevi Fountain and warp them and do over to render new views, and they're very nice. Except they don't have any capacity to model time-varying appearance. So they can't encode all the rich space of varying appearance of a scene over time. And there's no way to, therefore, interpolate appearance across time either. So we need to do something different. And so what we do is we devise this DeepMPI scene representation, where in addition to an RGB color and an alpha value, each voxel has a latent feature vector. Okay, maybe it's 8 dimensions or something. Okay, so every voxel has those components. And this latent feature vector is going to somehow absorb all the information needed to render a scene under varying appearance. Okay, so with this DeepMPI, and we also jointly learn a way to decode this latent feature vector to any possible appearance. Okay, so the way we fit these DeepMPIs to an actual scene, like our photos of the Trevi Fountain, is we first optimize a standard MPI. We fit the RGBA values to the scene. Okay, so we have our RGB MPI, and then we augment that with latent features and jointly fit those features along with learned neural renderer to learn the space of appearance for that scene. And this is fit. A new DeepMPI is fit for every scene you care to render. Trevi Fountain, Piazza Navona, Statue of Liberty, etc. So let me walk through those because I really like these visualizations. Okay, so to do that first stage, to fit a normal MPI to a set of internet photos, what we do is we create a plane sweep volume consisting where each plane we've projected and averaged all the images in our collection onto that plane. So what you're seeing here is kind of a focus stack sweep, a plane sweep, where for each plane in the scene, I'm projecting and averaging all of the internet photos onto that plane. So it sort of looks like this weird depth of field style focus sweep with you can think of it as a camera with a very strange aperture whose size is the size of the set of photos were in our collection. I think this is very beautiful. And even though these images are taken at all different times, what that means is this plane sweep volume gives you sort of the average appearance, like the lighting under the average, the appearance under the average illumination kind of looks like a cloudy day image, more or less. Okay, and so you initialize the colors in your MPI to these RGB values, and then you optimize the alpha and RGB to fit to the images in your collection. So you're kind of carving out the right alpha values and adjusting the color values to explain the images in your collection. Okay, you optimize the color and alpha in the standard MPI by rendering it to each input viewpoint and adjusting the values with gradient descent to minimize reconstruction loss. And even though these images, actually, I found this quite surprising and magical. Even though all your images in your collection are from different appearance, like sunny, nighttime illumination, this just kind of works to give you an MPI which captures the average appearance of the scene. This depth isn't, maybe perfect. It has a bunch of cracks and things in it, but if you render the alpha to a depth map and render this to an MPI, you get something that looks very, very plausible MPI under average appearance. Okay. Okay, so once you've done that, we have kind of a good initial guess for the alpha. We have a good initialization for the alpha values. We then learn we augment this MPI with deep features per voxel. where to render from this DeepMPI, the model is you warp it to a new viewpoint. Okay, so now you have a warped DeepMPI. You feed the layers through a generator, which converts that DeepMPI to a standard RGBA MPI. And okay, how does that generator know whether to render a nighttime MPI or a noon MPI? Well, there's a latent feature vector Z, which modulates how this generator works via an ADA-in, so instance normalization type approach. And where does that Z come from? Well, you can, for instance, use an exemplar image, like if, okay, I want to see a nighttime light field of this scene. You can feed an exemplar image into a learned encoder that produces that latent vector, which then says, okay, I want this MPI to look like this exemplar image. Okay, there's a lot of details into how to get that to work well, but which I'm going to skip. But once you've trained this, the idea is you can render a view. In fact, you can render that exemplar view with the MPI, and then compare it to the ground truth view, and that gives you a loss that you can use to optimize all of the elements in this. Optimize directly these deep features in your DeepMPI, optimize the generator and the encoder, etc. Just trying to reconstruct the images in your collection. And that works pretty well, and I'll show some results. So here's we created a data set. I think all this data is online if you want to play with this kind of problem for a bunch of different landmarks. And okay, you gotta do the Trevi fountain if you're doing, okay, sorry. I hit forward once too many times. Okay. Here we go. Okay, so here's the Trevi fountain rendered under 6 different appearance codes corresponding to 6 different exemplar images. And so spanning kind of day to night view synthesis appearance. Here's some results for the Piazza Navona. Again, kind of day to night, 6 different appearances. So you can render the scene under different appearance. And compared to other approaches that kind of preceded ours, in particular, neural rendering in the wild. Okay, one question is, do you decode each image each new view you want to render separately, or do you have a single scene representation that you decode to once and render from that for a given appearance? Things like neural rendering in the wild have a per view decoder, which those things lead to more instability in the in appearance over viewpoint compared to our method, where you decode an MPI and you can render any view from it. And you can decode any MPI for any. Once you bake the MPI, you can render from a fixed scene representation, and that gives you kind of very stable view synthesis. But you can also, it turns out that by fitting to all this scattered data, we also learned something that can reasonably interpolate between appearance codes. So here's 2 images under different appearance for the Pantheon. The sun's in a different position. And if you interpolate between those appearance codes and render different illumination, render the scene under different appearance, you get pretty plausible things like the shadows are moving in a fairly plausible way compared to, neural rendering in the wild, which gives you sort of more of a image space interpolate, something which looks a little bit more like an image space interpolation. Okay, so it seems like it's fair. Our method is fairly reasonably disentangling appearance in such a way that you can interpolate. Okay, and here's some examples where we're interpolating both in space, so new viewpoints, and in time, kind of fading to evening glow and the city lights coming on in the New York City kind of situation. Okay, so between the time when we submitted this paper to ECCV last year and when it was accepted, okay, NeRF appeared online, and NeRF in the wild, which is another paper on internet, sort of imagery, appeared. And so, a natural question is, how does this kind of MPI approach compare to NeRF-style coordinate-based representations? And so these NeRF-style, NeRF in the wild, which will appear at CVPR this year, they can render much larger changes in viewpoint because the MPI representation allows for only a limited kind of headspace style motion before you see kind of cracks between planes. But a disadvantage currently with these coordinate style approaches is just the speed of rendering. So to render, you have to evaluate MPI, MLPs along rays. Whereas for once you have an MPI, you can do real-time rendering in a web browser. And so currently there's that kind of trade-off. But I expect these NeRF approaches to get faster and faster over time. But I guess one kind of key takeaway here is like, okay, I've been working, and this is work with Rick, phototourism from 15 years ago. And if you just compare these side by side, we had very, very primitive image-based rendering for these internet photo collections back then. There's just been such like amazing progress on this rendering problem in the past 15 years, and to where I'm just completely astonished at the speed and the quality of current results. I say there is a lot of life, I think, in these MPI-based methods, though. So just yesterday, I saw online another CVPR paper called NEX from Supasorn Suwajankorn at Vistech in Thailand, which it's not like a DeepMPI. It's a different kind of model, but it shows kind of very rich appearance, very high quality view synthesis in this kind of head volume space kind of rendering. Even I'm very impressed by this like CD showing varying appearance under iridescence kind of effects. Okay, so I think there's a lot to be done in these MPI style approaches as well as coordinate style approaches. Okay, so you can check that work out and download the data at crowdsampling.io. Yeah, so I don't know if I should pause now or just steamroll ahead. This will be a natural time to take a few questions, but I can also just go ahead.
Yeah, please go ahead.
Okay, so I want to talk about one more project in detail, which is going from landmark scale to city scale. And this is with Colab. This is a Google project with Andrew Liu and a number of collaborators from Berkeley, Shiri Guinnessar, Tinghui Zhou, and Alyosha Efros. And so, okay, if you want to scale up this view synthesis plenoptic reconstruction problem to city scale, you kind of have a much different beast on your hands. So, okay, this is a photo of New York City. Imagine you want to dial up any photo at any place. Like you want to see what the Upper West Side looks like on August 28th, 2020 at 12 noon, or take a stroll down the Upper East Side at January 1st, New Year's at 4 p.m. How do you scale to this kind of problem? And there is an answer, which is there's an existing product called Google Street View Time Machine, which here's an example from the Flatiron. You can go there and look up all the historical street view from that place. Okay, so that's very cool, but that's very sparse. Okay, so the idea is, okay, from Google Street View Time Machine for any location, we can dial up a set of panoramas that are more or less taken from this place. And we have that for all of New York City and all of many cities in the world. But again, so over a course of 10 years, maybe, I don't know, maybe there's a dozen such panoramas. So very, very sparse. And these panoramas are not perfectly aligned. So the card doesn't like synchronize to the degree where it takes exactly the same photo as it drives around. Is much noisier than that. You just accidentally happen to take a photo that's pretty close to a photo you took in the past. Okay, and as a result, if you play these, if you play time machine data as a time lapse, it's very imperfectly aligned. Okay, this is an example from London, by the way, somewhere on the Strand. So you can think of this maybe as a wonky time lapse video. It's wonky in a couple ways. It's sparsely sampled in time. It's irregularly sampled in time, and it's not taken from a static viewpoint. Okay, so if we go back to this kind of plenoptic sampling plot, this kind of 2D time on the x-axis, viewpoint on the y-axis, a single run of street view looks something like this. For an hour, it drove through a city, captured viewpoints every 5 meters or so. Okay, and then maybe it revisits almost the same location 6 months later, 7 months later, a year later. And so you get this kind of sampling, which is a bit more regular, but very sparse. And if you compare it to those landmark photo collections, it's the scale of the data. If you look at Street View over an entire city, it's much sparser. Okay, covers a much larger area. It's much sparser in time too. We don't have, even compared to landmark photos, we don't have the same kind of temporal sampling. So in contrast to that landmark reconstruction problem where we could fit a representation per landmark, for this kind of problem, we somehow need to learn representations that generalize across places if we want to reconstruct a new view from any point in the space. And exactly that's what we're trying to do. We want to be able to compute any sampling in this plenoptic space. And so this almost looks like a sparse matrix completion problem, right? We have sparse samples in the space, and we want to complete the matrix of views. And so if you think about like matrix completion, you often arrive at the tool of using factorization. Okay, so we're going to pose this problem as a factorization problem where, okay, what we have is for a given location, we have multiple panoramas over time. And there's things that are fixed between those panoramas. There's things that are constant, like the building geometry, doesn't change very frequently. And there's things which change, like, I don't know, the lighting and the weather. There's also things like that change, like cars moving around, which we're going to ignore. Okay, but the weather and illumination changes. And so somehow we want to be able to come up with a representation where we factor permanent scene elements from things that change over time, like weather and illumination. Okay, and so if we could compute such a factorization and utilize such a factorization, we could then complete this matrix of this plenoptic matrix in the following sense. Given any image from any location in New York City or in the world, we could then, swap in a new, we could, while keeping the permanent factors the same, swap in new time-varying factors and render, I guess, any column of views in that plenoptic function by just swapping in all possible, temporally varying factors. Okay. So, so if you want to learn how to do this, if you want to learn a factorization from data, you arrive at sort of the classic ill-posedness of this enterprise, which is familiar to folks who have worked in things like intrinsic images. If you want to explain the appearance of an image in terms of kind of permanent factors and time-varying factors, like permanent factors being like the building reflectance, the underlying reflectance, and time-varying factors being like this shadow, you arrive at the problem of, okay, how do you know how much of these pixel values are explained by permanent factors like scene reflectance, and how much of them are explained by time-varying factors? How do you know that this is a shadow cast on this building and not a building that's painted with a shadow-like texture, right? They're all entangled together. And so from single views, it's very hard to get any kind of training signal to learn to disentangle, permanent factors and time-varying factors. But of course, fortunately, in our case, this is the beauty of Street View and Street View Time Machine style data. We don't have a single image. We have multiple images of the same place over time, as imperfect as this data is. And so we have a much richer set of data to draw on to learn this disentangling. Okay, and so for many parts of New York City, we have a stack of photos, a stack of panoramas from about that place. And if you mine Street View, you can come up with millions of these accidental time-lapse videos. I'll call these stacks. So millions of these kind of wonky time-lapse videos. And in aggregate, this data is very, very useful for learning this factorization that I'm talking about. Okay, so we actually built a data set from Street View where, around New York City, we took a set of regions as a training set and a set of regions as a test set where we try and predict how well we can do this separation. Okay, so how do we learn this factorization. Okay, so the idea is we want to somehow take image and encode it into a representation. But we don't want to, okay, we want to learn as much from data, just raw data as possible. But unlike on, maybe your autoencoders of the world, we want to put a little bit of structure in this representation, okay, to help it learn the right thing. And the structure is, we're going to structure it so that there's two parts of this representation, a time-varying part and a permanent part. And so the way this works is we have a stack of images, and individual images can get fed into this encoder to produce this representation. But the constraint should be that all of the stuff that's shared between images in the stack should be the same, and so the permanent factor should be the same for all the images in the stack. And anything that's different can go into this time-varying factor. You can almost think of this as like a compression problem. We want to compress the stack such that all of the anything that's shared between the stack goes into this permanent factor, and anything that's varying should go into this varying factor. Okay, so that's part of the structure we impose in this problem. And so we're going to learn these embeddings, and we're going to put just a little bit more structure on this factorization. And it turns out this is key. It doesn't work unless you do this. So we're going to separate this time-varying factors into two parts. One is just a general latent code, like, is very often used in these kinds of learned representations. So each image produces a arbitrary code that the learning can do whatever it wants to with. And then we're going to have another factor, which is, you can think of as a circular distribution. It's a distribution where the ends wrap around itself. And the key is that with a circular distribution, you can represent angles. Okay, and so you can think of this, in some sense, you can think of this as a heat map over possible 360 angles from 0 to 360 where the ends wrap around. And what can it do? Why would we include that? Well, it turns out that the most important factor is where the sun is. And if you can represent angles, even just one angle representing azimuth, you can capture sun, a factor that depends on sun position much better. And we don't tell it to use sun position. We don't give it timestamps or anything like that as supervision. It turns out that it uses this circular distribution factor it does indeed learn sun position with this factor. Okay, so that's pretty cool and interesting. And then, okay, so that's the time varying factor. We also have it learn a permanent factor, which is a spatial map. It is based on an image, a low resolution image. And this is meant to encode things like surface normal, surface reflectance, I don't know, material properties, like, is this a shiny thing? We don't impose any meaning on this except that it looks like an image, okay? But hopefully we'll learn those kinds of things. Okay, and then once you encode those factors, the idea is we're going to, and this is the last bit of structure we impose, we're going to decode them into a shading image. We're going to decode these into a shading image and a stack reflectance. So this is your kind of standard intrinsic images decomposition. There's going to be a decoded reflectance image and decoding shading images. And again, we're going to encourage the reflectance image to be the same across the stack. And the shading is free to vary across the stack. And the idea is then you can, by multiplying the shading image by the reflectance image, you can reconstruct the original input images. So we have this kind of autoencoder type framework with some structure in the middle. And this just works really well. And so we learn all these components, the factors and the encoder and decoder from these millions of images. And then you can apply this at test time to any new image. Here's a new input image. You can here's another new input image. So even though we trained it on New York City, it works for Paris too. Here's an image from panorama from Paris, where you can decode and resynthesize, relight images according to this decomposition. Now there's one more detail which is actually very important. Again, these are wonky time-lapse videos, so the reflectance image should not be the same. It should be, according to the exact viewpoint for each image in the stack. So for instance, if you average the images in the stack, because they're not taken at exactly the same viewpoint, you get this ghosting. And if you try simple things like, okay, so somehow we need to align these stacks. If you try simple things like RGB, congealing in RGB input space, it doesn't really work. And it doesn't work because the images have varying appearance. And so RGB, they shouldn't have the same RGB values if you align them correctly. But so the idea is a simple one. If we instead align them in reflectance space after we've done the decoding to a reflectance image, that alignment works much better. And now you have kind of a chicken and egg EM style problem where you iteratively learn how to decode reflectance and align images. And so here's a little, I guess, time lapse, if you will, of the process, this incremental process of learning alignment and reflectance. And you can see after this process, the alignment is much, these are again, averaged reflectance images. They look much more clean, like clean alignments. Okay, so how does this fit into this like plenoptic reconstruction framework? Well, again, so you can take two images. You can now, after you've learned this encoder, you can decode these time-varying factors, time-varying and permanent factors, and then you can decode the reflectance image for each one. But you can freely swap these time-varying factors and decode them to shading images. But in this case, since we've swapped them, we're computing shading under the other image's illumination conditions. Here I'll just show and then multiply them together. So here because we swapped, we're showing this image under cloudy illumination and this image under sunny illumination. You're kind of stealing the illumination of the other image. And this resynthesis by swapping factors works very nicely. Okay, so here's the original, and here's the two resynthesized image with the swapped illumination. Here's some more results from a different city that we didn't train on, where we just showed that you can take a new panorama in Paris and generate it under kind of arbitrary illumination, because this factorization lets you swap in any illumination you want to. And so the most natural comparison point is intrinsic image decomposition. Our method does something much more powerful, which is that it learns latent factors that can be swapped between images. Your typical intrinsic images takes an image and produces two images of reflectance and shading, but it's not like you can take that shading image and apply it to a new image from a different viewpoint. It's kind of locked to this image. But even as an intrinsic image kind of method, our learned factorization does very well. So here are some decompositions of this image into shading and reflectance from a few different methods. The second two columns are recent-ish intrinsic image decomposition methods. And the thing you want to look for is an intrinsic image decomposition what it should look like in this case is like, your shading image should almost look like the scene is covered in snow, like as if you painted everything white plaster color. And your reflectance image should not have any shadows or anything baked into it. And we see that our method achieves those kinds of qualitative properties, while other methods tend to have, the hardest thing is kind of decoupling cast shadows from reflectance and properly attributing them to the shading image. Okay, and so other methods have more trouble with that kind of problem, that kind of decoupling. Okay, so here's just a bunch of results where we now take a panorama and render a time lapse under all possible, over the course of a day. And you can see even the shadows tend to move fairly reasonably. Cast shadows are always the problem, and you can find more information here. Okay, so I just want to highlight a couple of very recent things we've been doing, sort of in this plenoptic or neural rendering space. So one paper actually led by Anju Kanazawa, who spent some time at Google. She's still at Google, working as a researcher, mostly at Berkeley now, but still working part-time with us. But she conceived of this idea of kind of taking an image and generating a whole world. So like, could you take an image and generate a plenoptic function from a single image where you could fly anywhere? And this led to this work called Infinite Nature, which is on archive now. And so the idea is that, compared to sort of standard view synthesis, where you can take an image and render small viewpoint changes, but if you try to render large viewpoint changes, you quickly reach the limits of that of view synthesis. Whereas our method sort of continually generates new content as you fly through the scene, so that you always see what is just beyond your you can always get content no matter how far you fly. Okay, so that's this Infinite Nature work. We have a data set of Coastline videos that we've run SLAM on, corresponding to this project that we trained this method on. And oops, yeah, I'll just quickly show some results. Sorry. So again, if you compare it to somewhat of an unfair comparison, but to standard kind of view synthesis methods that don't target large viewpoint changes, you can see that they break down fairly quickly. Again, they're not designed to do these kinds of large scale viewpoint changes, but it kind of shows the importance of this kind of generative aspect to our work. And we have this very cool flight simulator that Richard Tucker made, who works with me at Google, where you can like fly, upload your own photo even and fly through it infinitely. And you can click on where you want to go next. Okay, so I encourage you all to try that out. It's very cool. It's like, I don't know, one of my favorite Colab demos ever. Just one more thing, a teaser for a CVPR paper is this work we did with Elliot Wu, who was an intern with us last year at Google, on taking objects which are solids of revolution, like a lot of vases are in museum collections, and learning from single images to generate, to do inverse rendering where the result is a full 3D model with non-Lambertian appearance. So here, from a single image, we can generate these 3D vases which are shiny, and so you can render new views and relight them. And I don't know, I just want to show that because I think it's a really cool kind of capability. And I really like things that involve solids of revolution. Okay. So with that, I'll just end by saying we've been taking some baby steps, I would say, towards world scale view synthesis. And a lot of the, for all of this work, data is key. So having lots of images of landmarks and of cities, which can feed into these kind of factorization approaches, data is super important. But there's a lot of big challenges left to solve in this kind of space. So scaling up to the entire world, if you wanted to go anywhere, that's still a challenge. We're using neural rendering in a way where we don't have a physically based model of things like lighting and materials. And the way that maybe that comes to bite us the most is with cast shadows. Cast shadows are still very difficult to capture realistically, in my experience, from kind of purely implicit models. Oh, hi, Charlotte. Okay, Charlotte's here. I'll help you zip that up. Are you going outside, Charlotte? Okay, sorry, just bear with me for a second. Okay, this is Charlotte, by the way. Okay, see you. Bye. Okay. Sorry, I maybe should have mentioned we might see cameos. Okay. Sounds good. I'll see you after your walk. Okay, but I think actually the biggest challenge with this is that, I don't know, if you wanted to make a VR experience where you're sitting in the Pantheon, or you're sitting in the square cafe across from the Pantheon, everything that brings that scene to life is missing. What you would see is you'd see people milling around, you'd see clouds drifting through the sky, you'd see water in the fountain. Oh, I don't know, you'd see the lights come on at night. You'd hear the sounds of, I don't know, your people drinking coffee next to you, and the people in the square. And also, we're capturing, in the work I showed, we're capturing a very specific kind of temporal change, mostly illumination, right? So we're not capturing super small changes like the person walking through the square, like small time scale, and we're not capturing big time scale like the trees changing over the course of the year, or the weathering on the Trevi Fountain over time. And I think capturing more than just the single time scale is also a big challenge. So with that, I just wanted to thank the people who, the great collaborators on the main projects that I talked about, and thank you for your attention. Thank you very much.
Thank you very much, Noah, for a fantastic talk and deep insights. Let me start with a few audience questions. First, from Ali Osman Ulusoy. He has a few questions, but let me pick one. I have another question. Deep MPI capture day-night appearance changes very well. How do you think about capturing structural change over time?
Yeah, I think that's a good question. So there's one thing, something I didn't mention is that we assume that alpha is constant over time. So what the role of alpha in this MPI type model is mostly to represent geometry. And so we found it worked best to solve for alpha once in this first stage of optimizing an MPI, and then keeping it fixed for the deep MPI. And so I don't think we can do a good job of capturing any kind of geometric change. Perhaps you could also modify alpha, have alpha modulated in corresponding to some kind of time varying feature vector or something. So we didn't try that, but I think that would be very interesting. And I don't know, especially for changes, I obsess about trees. I think trees are the thing you would notice first. Trees change geometry over the course of a year. A lot of the scenes are pretty static, but I think that's a great kind of thought, and it's something we don't handle right now.
Thanks. I'll pick two more audience questions for now. This is from Daima Damon, our ICCV chair. Thanks
cool.
for
Thank you so much for your
as
service.
always. Is some of what we are doing now made harder by the choice of cameras, color space RGB? Will things be easier with HDR, multi-camera, capture, or advanced sensors?
Oh, that's an interesting question. So just to make sure I understood it, is the question, is the fact that, well, in the landmark case, we're using cell phones or whatever consumer cameras, is the question, are there better things we could be doing?
By more advanced sensors, HDR, photography, or multi-camera capture, or advanced sensors, or whatever advanced sensor that is?
Yeah, I mean, I think that's a great question. I mean, I would say like 8 years ago, I thought about this most in the context of these internet photo collections where, 8 years ago, I obsessed over things like, can we solve for the tone mapping of each individual camera in our data set? Because what at some level, what I wanted was like photometrically correct reconstructions where, according to some ground truth. But I think that's completely impossible from like tourist photos where cell phones are getting more and more creative about what kinds of processing is done to create a good looking image, to where I don't think it would be easy to consider a camera like most cameras as a photometer kind of device.
Another just comment from Nima. So do you believe, or do you think that the cell phone improves? That might help you, or you're more thinking cell phone improvement maybe doesn't matter for you?
Just to, I guess, respond to that and finish the thought was, I would say I've become less worried about like photometric accuracy and more concerned with just, does this give you a high quality experience? Like in some ways, I'm less a computer vision person in this respect than a computer graphics person. Just, can we reconstruct something that looks really good? I think with that, having better looking photographs to start with, like with better cell phone, is good. But I think as I think in some ways, like, I would still prefer people to have digital SLRs when they go around, just because I feel there's still a lot of limitations in cell phones can't capture that much light compared to digital SLR. But I'm not sure that that's a strong leg to stand on. Increasingly, like, I think the cell phones are perfectly good, and I don't have a lot of complaints. I guess HDR is interesting, but again, I feel like all these tricks, like, you know, bursts that cell phones are capturing, do a pretty good job of capturing even fairly, I don't know. Someone who thinks more about computational photography might contradict me on this, though. Like, if Rick or Ratul have any experience with the complaints about current cameras.
Yeah, thanks. So one more audience question. We
Yeah.
go to the panelists. This is from James Tompkin, I believe from Brown. Hi, Noah. Thank you for the engaging talk. Lovely findings and results. Is plenoptic representation enough? Are there reconstruction problems for which it isn't sufficient?
Well, I mean, I think the current formulation, again, everything I've talked about so far does not account for any kind of dynamics. So whether it's like changes in, you know, geometry over time, or even just the fact that the tree you're standing next to is waving in the breeze. I think, I mean, it's hard to say that something could be more general than the plenoptic function, but in terms of the actual algorithms we're using to reconstruct them, I feel as though one of the challenges I'm losing sleep over the most these days is handling dynamics in scenes. And you did see, I think you're seeing like a cottage industry of NeRF papers on that topic, but I think that's still an extremely hard problem. And especially if you're considering changes over every possible time scale, from, like, I don't know, your tree blowing in the breeze to the next ice age kind of scale temporal change.
Great, yeah, thank you. Thank you for the patience, Pratul and Rick. Maybe first, Pratul.
Cool. Yeah, thanks for the awesome talk, Noah. And I always like seeing these results. They're really cool. I really like this vision of like trying to like model the plenoptic function over really long scales of time. And I have a kind of question related to like how we seem to be tackling all these problems like right now. So like when you think about like small scale changes, like view synthesis and like changing like lighting where it's like very controlled, like if I'm going to move around some point lights around some object, it seems like all the best results we're getting right now are coming from like very explicitly modeling things. Like for view synthesis, our best results are like very explicitly modeling 3D geometry and how that reprojects in new views. Or like lighting on small scales, we're getting like really like the best results are like from explicitly modeling lighting and light transport and materials and stuff like that. But then like on the other hand, when we're talking about like these very large scale changes, like a city over to the scale of a day, or like weather changing, stuff like that, we've kind of like jumped to the complete other end. We're associating all these different points that we've observed with like latent codes and like trying to learn all the scale of the modeling. And I'm curious, like, how should we like be thinking about that? And like, what do you think, like, where did these come together? And what things are we like missing from being at either end of this spectrum, I think?
Yeah, I think that's a great question. And I think somehow morally or intellectually, or I tend to, despite the fact that this work is not using it, I tend to be more aligned with kind of explicit representations that allow you to do actual physical calculations of things. Like, I don't know, in the end, we should be doing like ray tracing, path tracing to render these scenes and to do these inverse rendering tasks. But I don't know, to me, it seems as though, and maybe this is what you're getting at, but the key question is how to combine sort of explicit representation of physics with neural rendering. So like, I would love to be able to reason about cast shadows in a very accurate way. I would love to be able to reason about inner reflections in a very accurate way. I would love to be able to reason about, I don't know, like standing in New York City, sometimes I see like I see highlights in the ground, which I reason must have, the explanation for those highlights in the ground is light bouncing 4 times off of shiny buildings and reaching me. And I feel like, somehow I want to be able to model those explicitly. But I feel like, so, I don't know, one guess is that the next generation of approaches will factor things in such a way that, I don't know, some things like cast shadows, for instance, might be handled explicitly by some kind of geometric reasoning. And some other things which are just very, very hard to model, like global illumination, might be captured with a more implicit, like neural rendering type approach, because it's just too hard to model all of that light transport in a way that you can learn with that. So I don't know, I'm hoping, I guess I'm hoping to see a lot of work that kind of explores combinations of those things.
Yeah, I think that's a really cool direction. Because like, yeah, I was also thinking it'd be nice to be able to like kind of set up in front, like, oh, these are the things I want to be able to explicitly model, and then try to have something that can recover as much of that as possible, and also give it like slack to explain wherever, like I've said, okay, these are the things I'm willing to like spend the compute or the time to like really model. And then a good way of like, yeah, can I just learn some slack to take account of like the other stuff that's not being able to, like not able to be modeled. Like, for example, if I like want to explicitly model like where's the sun in the scene and then use that to cast my shadows and do relighting, but like maybe I don't really want to model like all the clouds and the particles in the cloud and like light transport through clouds. So it'd be really nice like if we can figure out cool ways of like trading off between those two.
Yeah, totally. I have a question for the other panelists at some point, but maybe we could take that later.
Is Pratul, is that all your question for now?
Sure, I'm happy to go to Rick.
Yeah. I'd like to hear Noah's question because it sounds like there's a good conversation lurking in there.
Well, I guess so. I think I get a question a lot about trade-offs between things like MPIs versus more coordinate-based methods like NeRF. Mm-hmm. And I talked a little bit about it, but I'm wondering if, and also like one thing I don't know about is quality. Like, so I think there's a clear, like right now there's kind of a clear speed trade-off and viewpoint change trade-off, but I'm unsure about quality. So I don't know, maybe Pratul has thought about this the most, but I'm curious about, I guess, what people, maybe NeRF will be faster, maybe real time in 2 days because some archive paper will come out, or maybe it's already been real time. But do you think like, should I use MPI sometimes and NeRF other times, or will NeRF's kind of coordinate-based method win out? And how do you think about the trade-off? Maybe I'll ask Pratul that to start with.
Yeah, I think that's an awesome question. So like, in my mind, the most like compelling use of NeRF is at training time when like I don't know where the geometry is in a scene. I just have some images and I want a compact way, very, very compact way to represent like the possibility of geometry existing anywhere and being able to like do that with gradient-based optimization. But like once I've solved for a scene as a NeRF, like at test time, it's less compelling to still like fix myself to using that NeRF, right? And you can imagine tons of ways of like baking something out of that trained NeRF to that may be able to be rendered in real time. And like, for example, MPIs, because of the way they distribute like geometry at image resolution, like in like disparity along a frustum, they're very good for rendering a certain like range of viewpoints very, very efficiently. And so like you can imagine the same thing, like I solve for something represented as a coordinate-based representation as a NeRF, but if I only want to render these viewpoints, I bake out an MPI for my NeRF or something like that. So I think we don't necessarily have to like fix ourselves to using one representation always. I think it depends on like during optimization, during like if I want to be able to render stuff fast, we can kind of, I think we want nice ways of flexibly moving back and forth between these without like losing too much. But that's kind of how I think about that.
Well, I can ask a quick follow-up, which is, or is it going to be, does it just mean that NVIDIA needs to invent a NeRF renderer and that will solve like a hardware accelerated NeRF? Or is there a reason why that can't work and shouldn't work?
I think there's definitely a lot of like juice left in making volume rendering faster with like the tools we have available. I think like the current incarnation of NeRF and like how it's implemented isn't like taking advantage of a lot of things that even exist within like the graphics world for making volume rendering faster. So like that's still all on the table. We could kind of take advantage of that. And I think so at the same time, I think we're others seeing like a lot of like follow-ups on NeRF for like making really cool ways of accelerating how you render NeRF during like even training times. So, like there's ways like approximating integrals through NeRFs and stuff like that too. So I think it's good to kind of co-evolve both of these, and then, but I think, yeah, so I think even if you care about really fast rendering, it's hard to imagine a very like a coordinate-based volume representation like NeRF really being the end answer for like very fast rendering and test time. But I'm really curious to hear Rick's thoughts about this stuff too.
Yeah,
sure.
and
I've been mostly reading the literature. I haven't actually implemented or published any papers in this area. It's a great question, Noah, because I was going to ask you that one, but I think probably you and Katul have a ton of experience in this. And, Noah, you've been a co-author on the NeRF++ paper, so you know them as well, right? And that paper was a collaboration with Vladlen and his students and colleagues. So, we've mentioned the conversation, this conversation we're having is fascinating for me. I just finished a neural rendering section in the second edition of my book. So it's a huge field. So I basically only have 1 to 2 sentences to devote to each paper. But in addition to MPIs, there's the coordinate-based techniques like NeRF. There are layered meshes, right, which are sort of like an MPI from Michael Broxton and those people, where you use fewer layers than LDIs, right? And then there are even more classical things. You haven't mentioned the IBRNet archive paper, right, which just came out. And some of Vladlen's work, the latest of which that I've seen, there might be newer ones, is the stable view synthesis, which is really a traditional 3D mesh model with a better kind of surface light field neural renderer on top of it. So there's a fascinating range of representations available. For those of us who know graphics hardware, we know that things that are closer to a triangulated mesh model will render more quickly, just because the number of things you have to put onto the screen is proportional to the surface area rather than the volume, right? But we don't have any really good evidence that fuzzy things work well. So the tanks and temples is all very hard metallic stone surfaces, right? So on those data sets, these mesh-based models do well. On things that are fuzzy, other things, volumetric-like things do better, right? Then there's the whole question of reflections, right? And MPIs model reflections to a certain amount, by having ghost images at a different depth. NeRFs do it by having viewpoint dependent effects, which is good for modeling the shiny bumps on a Lego bulldozer, but I'm not really sure. I guess there have been a couple of NeRFs which have real reflections, like on windows and things, right? But it's not obvious that that's a great fit, right? So there's this fascinating space of, depending on the object, depending on the viewpoints you want to render it from. And then, of course, there's the manipulation question, right? Do you want to change the lighting? And so NeRV with the V at the end is a beautiful piece of work in that area. The tutorial on neural-based rendering is wonderful, and the state-of-the-art report that Tawari is the first author is great, but it's already so dated. I think maybe Yasu should organize just a panel on the latest year of neural rendering papers that have appeared in archive. I'm sure some of them will appear in CVPR this coming summer, and have a real discussion just to see if we could sort of have a shootout of in what situations you think that one thing would be more appropriate, right? So the intuition that Bertul has that the coordinate-based techniques are wonderful at reconstructing is what I've heard other people say as well. I think John Barron is in the mix with a lot of these things. I haven't actually seen a head-to-head comparison on a data set where you run, let's say, a classic Colmap. I'm not sure what Vladlen uses to build his initial meshes. But for a data set like that, and we know that I believe the MLP reconstructions are slow. They use stochastic gradient descent as opposed to something like a multi-view thing. So just do a shootout on quality and speed of reconstruction. So I completely agree that it's okay to sacrifice reconstruction time and then post-convert it to a faster renderer. But I'm not even convinced yet of which technique gives you the best reconstruction, right? There is this big spread of the things that feel more classic, which I would put sort of the stable view synthesis in that category, because it does commit itself to a single mesh, right? And at rendering time, the neural renderers seem to have a lot of advantages. Rather than pushing colors around, you push codes around, which somehow capture local something or other better, so that the final renderer doesn't have weird artifacts, right? Because you got one pixel the wrong color. The neural renderer will kind of make it look reasonable. This is a brain dump, but it's a fascinating, very fast-moving field.
So I don't know. I have more questions for Rick actually, but I don't know. Is that allowed, Yasu?
Yeah, sure. Yes.
I mean, and I don't mean to put you on the spot, so feel free to not say that you've not thought about this. But I mean, since you have written the textbook, and now you have a neural rendering chapter, which I really look forward to read, but you probably have chapters on classic methods. I mean, these, like the MPIs, well, it's actually the stacked acetates from the 1998 paper. I'm wondering if there are top secret things that your favorite methods from the past that we should be revisiting. I don't know, the sprites or layered depth images, kind of, or layered.
It's a great question, but I think all of the good ideas have been revived. Like even the stable view synthesis, which basically puts neural codes on the surface of the mesh, right? It's an alternative to the surface light fields. The first version, the original archive draft of that paper doesn't mention surface light fields, but I sent an email to Vladlin, so he's going to put in a comparison. I think a lot of these things are being rediscovered. So the sprites, again, the Gelato paper that Ricardo and others were authors on, right, uses this idea of flat layers. And again, it's a great description. Really, the best description for something like the eyeglasses I have is a bunch of flat little layers with alpha transparency are great, right? So I think we're going to start seeing hybrid methods. I mean, computer graphics artists, game developers are not at all shy of throwing together, large flat objects for backgrounds and, whatever they need to, and a little bit of volumetric rendering, right? So I think as an engineering perspective, if we want objects to be, to capture with a relatively small footprint and small rendering time, we may have to adapt the representation to the object itself and to the range of viewpoints and how much you want to relight it. And if you want your object, you've captured your ceramic vase in the latest CVPR paper I hadn't yet seen, right? And if you want to drop it on the floor and bounce it, I mean, if it's ceramic, it'll shatter, but if it's metallic, it'll bounce. Then you need something closer to an actual finite element model that will allow you to do animation, right? So I think the classic techniques we saw in computer graphics that were developed 20 years ago made their way into beautiful CAD and simulation tools, right? That mechanical engineers now use and artists at Pixar now use and things like that. So I think the exciting new, neural representations will slowly get into tools that will hopefully be interchangeable. I think the current state of the art is each paper is sort of a pure approach with its own pure GitHub repository, and then it downloads the other people's codes to have the classic 2x2 diagram of R's versus A, B, and C. And ours always looks better. But sooner or later, clever people are going to put these things into actual animation toolboxes. And then eventually the artists will figure out which things are good and which time. And there'll be all these talks at SIGGRAPH about secrets of neural rendering and how you use this tool for this effect and this tool for that effect. So this is my wild speculation of where the field is heading, right?
Cool.
I'm no expert on these. I used to do image-based rendering, not anymore. I'm more in geometry now. But I now feel exciting. This is my outsider's view. I wonder if you agree. So NeRF was to me revolution. General MLP or machinery, no geometry, no prior, just an algebraic approximation function. And MPI is like putting some hint of our structure, layered representation, to kind of bring in classical principles of image-based rendering vision before deep learning, and allowing a bit of variation to be learned by the deep learning. But we trying to use domain knowledge to shrink as much as possible, then letting the only necessary variation to be learned by the network. I wonder if that's also, you agree, that's the direction after NeRF comes in. And next, by Spasson is also like that. Layered representation, much faster, better. I wonder if you agree, and this is a direction where many people may go to for publishing papers from now.
I'm not sure who you're asking, but
yes, I'm asking, is that what you feel? Basically taking the MLP style thing and use domain knowledge to somehow design structure of architecture? So this is the audience question. Eric, next timer, related. If you really want to scale up to city scale, neural rendering, do you do more like a per local MLP style, a per local MPI? How do you do? It's not just one MLP, everything. You may want to have some structure to kind of shrink the space, then learn.
That's interesting. Sorry, but it's it's hard to tell who people are looking at when they're asking questions. So yeah.
Well, I'll just jump in because I'm not sure I've caught every recent neural rendering paper, but I did my best to catch the interesting ones. So, if you ask me can you do this and that, the combination of the use of implicit functions, whether they're MLP based or other things like, classic sign distance functions over a large domain, there have been a number of papers that say, look, if we have a large space like a whole house, let's decompose it into separate rooms, or let's do a 2D floor plan decomposition and then kind of represent the local functions within a cell, right? It's a hack, but it's a very it's an old hack which has to do with things like octree decompositions and so on. So I think one answer, if the person asking a question isn't familiar with it, is to look at the papers where you sort of do a spatial subdivision and overlay it on top of, and then use implicit or neural representations internally. Hi, Charlotte.
Rick just said hi to you, Charlotte. Sorry, she can't hear you, but yeah. She's a little annoyed at me. Sorry. I'm sorry, I don't mean to put you on the spot.
I just want to quickly add on to what Rick said. I think it's I totally agree. It's a lot of value in baking in a little bit more structure on where content actually exists in the 3D world if you have that as prior knowledge. And it actually even exists in NeRF, within the ways that we represent forward-facing scenes. We're not sampling space isotropically. The sampling structure is actually very much this normalized device coordinate sampling structure for these scenes are face forward. It's actually very much MPI and Fresnel sampling inspired, right? Because you're essentially making a NeRF that's sampled with a density that's proportional to how MPIs decide where to allocate samples. So that kind of baking in prior knowledge of where the content actually exists in space and where you want to represent the content to render the views that you care about rendering is a very important kind of thread that runs through a lot of these methods that even feel more unstructured.
Yeah, sorry, I somehow interpreted part of that to include things like primitives of planes. And so maybe planes are something that MLPs can do. But there's also, cylinder, every so often these primitive-based ideas come back into vogue in computer vision. Planes, cylinders, spheres. I don't know if we've
thought much about it. It's too bad we can't have there's a lot of people who've worked in the whole NeRF space, right? So, but immediately John Bergen comes to mind, as someone else who'd have something interesting to say. If you look at the math under an MLP, and if it's a classic ReLU nonlinearity, right, you're really talking about linear subspaces, linear hyperspaces that you then combine in a weird additive fashion. So obviously representing a plane in a coordinate-based system is trivial, right? It's just a linear equation. But now that you've represented it, how do you combine it? The thing about constructive solid geometry is the mathematics is very well defined, which you're allowed to do, right? You can union, you can subtract, and so on. The same thing with back to front rendering of primitive geometry, right? You basically have Z-buffer overing or whatever you want to call it, right? But right now, the MLP under the hood, the current coordinate-based techniques use a classic over ray tracer to composite things, right? But how they decide to sort of combine the weights and the activations in different layers to come up with a decomposition is very much a black box. So it might be that putting in other primitives, to my thinking, the whole neural network crowd is a little stuck in this linear combination plus ReLU, formalism. It's nice, you have to design the constraint space, right? Otherwise you'd start, exploring the space of activation functions, and people have published papers about that. But it does seem like if you want to, like with your work, Noah, on the factorizing, right? You made a decision that you were going to produce 2 images and then multiply them, right? So you're putting structure into a network, which could have been just one end-to-end goop. And you got better results by putting in sensible structure that mimics the way light interacts. So I think we may see eventually things like MLPs being, composed into different things. And even the NeRF work now, right, with the viewpoints has a very particular way of rendering, which is, after you bounce the ray in a certain direction, you have a termination depth and things like that. So yeah, I'm not sure we'll get to the point where Yasu might have been suggesting that we'll actually have primitive geometric elements in there, but we'll see.
Well, maybe, it's hard to really cut the discussion, exciting discussion now, but it's about time for Noah to maybe go back to play with their child. I'd like to thank again, Noah for the great talk, Pratul, Rick for the discussions, questions, and audience for the questions and joining us. We'll take a week of break, ICCV next week. We'll be back 2 weeks from now to Asia this time. So thank you very much again, all, and have a nice day.
Great seeing you
Thanks
all.
for putting this all together. Yeah, it was really fun.
This is so cool.